We've already seen adding functions before. Some things I want to remind you of: there's the one type of notation, there's the other type of notation. Whenever you have that second notation, I recommend changing it to the first notation so that you're more familiar with it. Okay? If we look at the graph and the domains that we get, one thing I want to point out is, since there's a restriction on our red functions domain, that will always result in the same restriction on the graph that you get after adding, which is our green function. Again, if you had f of 2 plus g of 2, sometimes this shows up like that, f plus g of 2. And if you had that, I would switch it first to this and then figure out f of 2 is 2, g of 2 is minus 1, sorry, and 2 plus a negative 1 is equal to 1. So again, what are we doing? We're adding our y values. When looking at subtracting, same thing. Here's the normal notation, here's the other notation. Get used to both of those. And same thing with adding. If, as we have in this case, our red function is restricted, that will mean that our green function would be restricted as well. Again, just add corresponding y values with the same x coordinates. And finally, same thing happens for multiplying. Good notation, not so nice notation. Same pattern. If one of our functions is restricted, or if both of them are restricted, then our new graph would be restricted as well. I mean, if you had one parabola this way, another parabola this way, when you multiplied them, they would just be in between here, not on either side. So now we're going to look at our first example. Our first example, we have f of x being a line and g of x being the absolute value of x. So one of the things that you might do here is you might just say, I know what a line looks like. I'll do that one in green. I know what the absolute value graph looks like. I'll just draw a quick sketch of each of them in blue. So when I get to part A, which says state the domain and range of each of them, well, for my green graph, that's a line. I know that its domain is everything and its range is everything. For the blue graph, which is my absolute value graph, I know that my domain is everything, but my range is bigger than or equal to 0. Part B introduces some important terminology. It says write an explicit equation. So at this point, if you don't know what an explicit equation is, doesn't matter how good your math skills are, you won't be able to answer this question. So one of the things that's important in any subject area is learning the language and understanding what different terms mean. In this case, what is an explicit equation? An explicit equation is an equation that is just in terms of x. So currently I have h of x is f of x plus g of x. This is not an explicit equation because on the right-hand side of my equation, it's in terms of functions, f of x and g of x. If I want to write it as an explicit equation, I need to write it in terms of x only. So what can I replace f of x with? I can replace that with x plus 2. What can I replace g of x with? I can replace that with the absolute value of x. That's an explicit equation. Determine its domain and range. The easy one is the domain. When you look at the explicit equation, are there any non-permissible values in that equation? If there isn't, which there isn't, then your domain is everything. The range, though, is a little bit more difficult. To figure out our range, we might have to look at our graphs. So I'm going to draw my grid here. Originally, I had made my line green, so I'll draw that in green with a slope of 1. And I drew my absolute value graph in blue. So if I wanted to add these two functions together, I could just take corresponding points and start adding them. So start adding points. I'll go from left to right. At -3. At -3, I have a -1 value here and a +3 value up here. 3 plus a -1 would be 2. Here I have 0 plus 2, 2. 1 plus 1, 2. 0 plus 2, 2. 1 plus 3, 4. 2 plus 4, 6. So I've done a couple of points. Looking at the pattern, it appears that it stays always at 2 on this side, and it goes up on this side. So looking at my graph, based on the points that I've done, and assuming that it stays the same, it looks like my range is y is bigger than or equal to 2. Now on your exam, they usually ask only domain questions. If they ask range questions, you'll have to be able to work with the graphs. I'm going to show you algebraically how you would figure out that equation for that graph. Yes? Yes, a lot of stuff that just says, here's two graphs, can you add them together? Here's two graphs, can you subtract them? And then you're just taking corresponding points like we did with the blue and the green graph and add them together and subtract them. Okay? But what I'm going to teach you right now is something called piecewise functions. And it can be used algebraically to see why the black graph is the graph that it is. Now, the most common piecewise function there is the absolute value of x. And that's written as an explicit equation. The way that it's written right now is not in piecewise function notation. But what piecewise functions mean is when you can take a graph and say, hey, the graph looks like it's two different equations in two different pieces. For example, the black graph, can you see that it sort of looks like there's one line at one part and a different line at a different part? So you could describe it as two different graphs. And that's what a piecewise function does. It says, look at your absolute value graph in blue. Does it look like two different lines? Yes. It looks like one line when x is bigger than or equal to 0. So in a piecewise function, there's always a domain that's stated, and one line when x is less than 0. And then you describe each piece. What's the equation of this one, which I'll highlight in yellow, because that corresponds to this part of the domain. What's the equation of that line? It's a straight line, slope of 1, y-intercept of 0. Well, that's just your basic y equals x line. And this one, which I'm going to highlight in green, this part of the graph, what's the equation of that line? It just is a negative x. Still has a y-intercept of 0. And so this is how you would write an absolute value equation as a piecewise equation. Now what we're going to do next is take h of x, and instead of writing it as an explicit equation like we did, we're going to write it as a piecewise function. Now h of x, see if I can scroll up to see it, is x plus 2 plus the absolute value of x. And I'll just rewrite it here so we can see it. It's x plus 2 plus the absolute value of x. When x is bigger than or equal to 0, the absolute value of x is equal to x. So if I did x plus 2 plus x, this equation would become 2x plus 2. When x is less than 0, the absolute value of x is negative x. That's my definition from my piecewise function here. And if I did x plus 2 plus a negative x, the x's would cancel and I would just get 2. And now that I've written it as a piecewise function, does the black graph really match up? When x is less than 0, is it just y equals 2? Yes. When x is bigger than 0, do we have a line with a y-intercept of 2 and a slope of 2, up 2 over 1, up 2 over 1? Yes. So writing this one as a piecewise function can really help us see what the graph looks like. When we get to Part C, Part C says write an explicit equation for the product of the two functions. So they say p of x is f of x times g of x. So the explicit equation would say, well, f of x is x plus 2. G of x was the absolute value of x. That's our explicit equation. Again, we can just look at that equation and say the domain. Is there any non-permissible values? No. The domain would be everything. If we wanted to find the range, we could use the graphs. I am going to use the graphs that we had here. Okay? We had our absolute value graph, which is now highlighted, and our line. I will graph the x squared graph on top of it. If you multiplied things, okay? 0 times 2 would be 0. 0 times 2 would be 0. 1 times 1 would be 1. 3 times a negative 1, negative 3. 1 times 3, 3. 2 times 4, 8. So we take corresponding y values and multiply them. And once I have those points, based on what I see here, you might draw this graph, which is pretty close to the right graph. We've just drawn a lot of points, and we joined those points, and that is very close to the right graph. Why it's not quite perfect, I'm going to show you using the piecewise notation. Okay? So if I do p of x in piecewise notation, oops. Again, we would break it up when x is bigger than 0 and when x is less than 0. When x is bigger than or equal to 0, the absolute value of x is just x. So if I would multiply x times x plus 2, or I could even leave it like that, it would be x times x plus 2, or x squared plus 2x. And when x is less than 0, the absolute value of x is negative x. So if I multiplied that out, it would be negative x times x plus 2. Now I'm going to leave them factored because it's going to help me graph. I'm going to graph this one in green and this one in blue. They're both parabolas, and because they're in factored form, I know that the x-intercepts of this green one will be at 0 and negative 2. This would be x squared plus 2x, which is a parabola that opens up. And I'm just going to graph that parabola with a dotted line right now. That is x squared plus 2x the whole graph. In blue, I'm going to graph negative x times x plus 2. It has the same x-intercepts. But can you see if you multiply it out, you would get a negative x squared, which means that parabola opens down. And that would be the graph of negative x squared minus 2x. So how do we figure out what p of x looks like? I'll do p of x in purple. P of x says, take the green graph, but only the piece when x is bigger than or equal to 0. So on my green graph, I have only that section. Then for p of x, it says take the blue graph, but only the piece when x is less than 0. So on my blue graph, I would take this section. And this is almost identical to the graph that we found just by multiplying the points. A little difference, and what makes this graph more accurate than the graph that we drew, is do you see how there's like a sharp point at 0? Whereas on the graph before, we kind of made it look like an x cubed graph where we made it smoother. We wouldn't have known any better. Based on the points that we had when we multiplied them, they would accept that x cubed graph if that was the technique that you used. But now we can see that here there is a sharper point at 0. So a little bit different than an x cubed graph. Because in piecewise notation, we're taking two parabolas and putting them together. Okay, questions for practice? 3, 5, and 10. Oh, and by the way, now that we've drawn our purple graph, we can say from the graph that the range is everything.